Hello everyone, welcome to this 22nd lecture in the NPTEL course on Riemannian geometry. So in the previous lecture we computed the curvature tensor for these model spaces m kappa comma g kappa. So these were basically when kappa is positive, this was the round sphere of radius 1 by square root of k. When kappa was 0, this was the usual Euclidean space, and when kappa was negative, this was the hyperbolic space of radius 1 by square root of minus kappa, right. Okay, so today I want to explore zero curvature a little bit more. So of course from the analytic point of view, zero curvature just means that the covariant derivatives commute, but I want to give a more geometric interpretation to this condition of zero curvature. Okay, so that is the content of today's of this lecture. So the key definition is the following. So a Riemannian manifold is called flat if the curvature tensor vanishes identically, okay, or equivalently the curvature endomorphism vanishes identically. Okay, so what are some standard examples? One, of course, the Euclidean space, but by naturality we have seen that these tori, which we have quite conveniently also called them flat tori, we call them flat tori precisely because they are examples of flat Riemannian manifolds. Okay, so these are of course also examples of flat manifolds. In today's lecture I want to actually give a complete characterization of flat manifolds. So here is the main theorem that I want to prove. Okay, I want to claim that Mg is flat if and only if Mg is locally isometric to the Euclidean space. So what does locally isometric mean? One has to be a bit careful here. So let me spell out what I mean by this. That is, for all points P and M, there exists a neighborhood U and a diffeomorphism phi from U to some open set sitting inside Rn, such that if you pull back the Euclidean metric from this open set via this map phi, then that is precisely G, okay, G restricted to U. Or equivalently what this means is that there exist coordinates x1 up to xn such that the metric tensor is Euclidean on all of U. So note that we can always find normal coordinates so that this equality happens at one point, right, but flatness actually implies that one can choose coordinates so that this equality happens on the entire coordinate patch, okay. So one important word of caution, this does not mean that there is a local isometry phi from either to mg as in the case of the flat tori or vice versa, or in the reverse direction. Okay. So of course in each of these special cases the resulting, I mean, Mg will be flat, but for a given sort of flat manifold it is not always necessary that that there is a local isometry, or at least that is not what is being claimed by this theorem. Okay. So being locally isometric to Rn is different from there being a local isometry from Rn to M comma G. Okay. So that is a little I mean, you have to be a bit cautious with this with the meaning of locally isometric. Okay. So in any case, so the aim is that given a flat manifold I want to produce coordinates so that the metric tensor is identically the Euclidean metric tensor in those coordinates. Okay. So the key input that we need is the following, is the so called Frobenius's theorem. So this is a standard theorem that is discussed in all books on smooth manifolds. So I am not sure if this was covered during the NPTEL course on smooth manifolds. I mean, I know that there is an NPTEL course given which was provided by my colleague on smooth manifolds, but I am not sure if this theorem was actually covered in that. If not, as I said, you will find it in any basic textbook on smooth manifolds, for instance Warner's book or Lee's book and so on. Okay. So what does Frobenius's theorem say? So let V be an open subset of M, and let x1 up to xk be some vector fields on V, okay, such that they satisfy this key condition that their Lie brackets, mutual Lie brackets vanish for all ij. Okay. Then for all p in V there exists a neighborhood U of p with coordinates such that these vector fields xi's are given by coordinate vector fields. So xi is given by del xi for all I from 1 up to k. Okay. So note that this in particular implies that k has to be less than equal to n. Okay. All right. So we are going to use this theorem in a crucial way. We also need another input. We also need the following lemma. So since there are going to be multiple lemmas, let me call this lemma 1. So let us say I have a smooth curve. So if gamma is a smooth curve, and let us say x is a vector field along gamma, is a smooth vector field along gamma, such that x is parallel, which means that this covariant derivative in the velocity direction of x is identically 0. Okay. And suppose at some point x of t naught is 0 for some t naught, then this implies that x of t is identically 0. The proof is rather simple. consider the trivial. So the proof is basically just by uniqueness of parallel transport. Because x is parallel, x at t is precisely the parallel transport from t naught to t of x naught, where x naught is x of t naught, but we are assuming that x of t naught is 0. So then parallel transport is a linear map, so this is going to be 0. So this implies that x of t is going to be identically 0. Okay. This particular statement that x of t has to be given by the parallel transport is because of uniqueness of parallel transport. Okay. Alright, so that proves the lemma. So now let me prove our main theorem. So our theorem, if we go back to it, is an if and only if statement, that Mg is flat if and only if it's locally isometric to Rn, right. So there are two implications that we need to prove. So let's first prove the reverse implication, that's the easier one. Suppose this is locally isometric to the Euclidean space, then for all p there exists a neighborhood u and a diffeo from u to phi of u such that the Riemannian metric G restricted to u is simply given by the pullback of the Euclidean metric. Okay. But then by naturality the curvature tensor restricted to u is also given by phi star of the curvature tensor of the Euclidean metric, which we know is 0, right. So the metric on u will also have 0 curvature. But now this happens for an arbitrary point p, and so the curvature tensor must vanish for the entire Riemannian manifold. So this proves the easier direction. So let's prove the harder direction, namely the forward direction. So we first have the following lemma. So this is the second lemma in the proof. For all points p in M, there exists a neighborhood V with an orthonormal frame which I will call E1 up to En of the tangent space such that the covariant derivative of each of these EIs is 0. So when I write the nabla EI is 0, that means that for all vector fields on V, nabla x EI is 0 for all I. Okay. So let's prove this lemma. So note that it's actually it's enough to show so maybe I'll get back to that later. So this is the main lemma that we want to prove. Let's assume this for now and then complete the proof of the main theorem. So assuming this, let's complete the proof of the main theorem. So now what is by torsion freeness, if you take the commutator of EI and EJ, so this is by torsion freeness of the connection, this is the same as this. Okay. But then by construction, since the covariant derivatives of these vector fields vanish with respect to any vector field, this is going to be 0. So that means I now have a frame of commuting vector fields. So then by Frobenius, there exists a neighborhood U of P with coordinates x1 up to xn such that EI is given by the standard basis vector del I, right. This is where I am applying Frobenius. But then if you look at Gij, that is the inner product of del I del j, that is the inner product of EI Ej, and the lemma says that I can construct these EI up to En to be an orthonormal frame. So this is obviously then going to be delta Ij, okay, and this completes the proof of the theorem. This is what I was claiming in the theorem, right. Okay, so basically it's enough to prove this. Okay, so let us prove lemma 2. Right, so it's enough to do the following. There exists a V with coordinates x1 up to xn and an orthonormal frame E1 up to En such that if you compute the covariant derivative of EI with respect to del j, that is 0 for all I and for all j, right, because any other any x can be written as xj del j, and then by R linearity this will simply be xj del j EI. So if I have already shown that these are 0, the result will also be 0, right. So it's basically enough to produce coordinates so that this happens and an orthonormal frame so that this happens. Okay, so how do you do this? So let W be a coordinate neighborhood of P, right, and such that so let us say with coordinates x1 up to xn, and I can always scale the coordinates so that the cube Q, which is the set of all points with coordinates x1 to xn, so that xi is less than 1, this is contained inside W. Okay, so then in the end I am going to set V to be equal to this cube. Okay, so let me draw a picture and explain how to construct these EIs. So let me draw a picture of a cube, not the complete cube, but but maybe an open sort of version of the cube. Right. So, I am not writing out the other, let me maybe draw a better pic. Okay, so so now I am going to do the following. So, I am going to assume that my point P is at the center of the cube, and I am first going to look at the following. I am going to look at this x1 axis. Okay. So, the first step in the construction is the following. So, so we pick E1, little e1 up to little en be an orthonormal basis for the tangent space at the point P. Okay. Then let EI of x1 0 0 etc. be the parallel transport of the basis vector EI to the point x1 0 0 0 along the x axis, along the x1 axis. So, I have denoted the x1 axis with the blue line. So, at this point you basically have the E1 vector and the E2 vector, right, and the E3 vector and the En vectors. So, you essentially just parallel translate along that axis. Okay. So, you will get a frame at each of these points. Okay. So, note that by doing this, this is an orthonormal basis for the tangent space at the point whose coordinates are given by x1 0 0 etc. up to 0 of m. Okay. Then at the next step I basically use the tangent vectors here and extend them along lines parallel to the x2 axis. So, in the second step for each fixed x1 so parallel translate EI of x1 0 up 0. So parallel translate along the line through x1 0 0 etc. which is parallel to the x2 axis, and this way we can obtain a vector EI of x1 x2 0 0 etc. Okay. So, now inductively you just repeat this process. So, inductively repeat. Okay, so then in the end we obtain an orthonormal frame E1 up to En on this cube Q, right. One thing to note is that one has to actually check that this does give you a smooth frame. So smoothness, I mean each of these vector fields are actually smooth, and this actually uses the fact that parallel transport is a solution to a linear ODE, so it varies smoothly on the initial conditions. So smoothness follows from the smoothness of solutions to linear ODEs, or rather I should say smoothness of the dependence of solutions of smooth ODEs on initial data. So if the initial data varies smoothly, the solutions will vary smoothly. Okay. And we get orthonormal frames since parallel transport preserves inner product. Okay. All right. So now my claim is the following. So let Sk be the slice given by the vanishing of the final n minus k components, right. So then on Sk, my claim is that if you take the covariant derivative of Ei with respect to del j, this is 0, where j varies from 1 to k and I varies over the full set 1 to n. Okay. So assuming this, we are done. Since on Sn, note that Sn is the entire cube Q, we would have that the covariant derivative of Ei with respect to del j is 0 for all j in 1 to n and for all I in 1 to n, which is exactly what we had to show, right. So it all now boils down to proving this claim, right. So let's do that. Okay, so the idea is we do induction on K. Okay, so the key observation is the following. That on Sk by construction, because remember in the final step we basically parallel transport in the kth step, we parallel transport along lines parallel to the xk axis, right. So then by construction, if you calculate the covariant derivative of Ei with respect to del k, that's 0, that's just by construction. Okay, so now how do I use this? So in induction, of course, there is first the base case. The base case is when k is equal to 1. Okay, but here on S1 by the above observation, this is anyway 0. Okay, so and that was exactly what was being claimed in my claim, right. So that settles the base case. So what is the inductive step? So in the inductive step, suppose I assume that the claim is true on Sk minus 1. So what this means is that all of these derivatives is 0 for all j from 1 to k minus 1 and I from 1 to n, and this happens on Sk minus 1. So now we want to establish something like this on Sk. So note that if you take the jth standard basis vector and the kth standard basis vector, then their Lie bracket vanishes, right, for all j from 1 to, let us say, k minus 1. So this means that right, so on the other hand, by the observation, if you take this is identically 0. So even if you take a covariant derivative with respect to del j, that is going to be 0. So this is by the observation, the key observation in blue here. Okay, but then by definition of the curvature tensor, that is precisely this. Plus the curvature tensor applied to del j, del k applied to EI. So now I finally use the fact that I am working on a flat manifold, so this is 0. This is precisely the definition of flatness. Okay. So the upshot of all this zero for all j from 1 to k minus 1 and for all I. Okay. Now let us look at the situation. So let me draw maybe a picture. Let us say this is Sk minus 1 and this entire thing is Sk. Okay. So consider these lines that are parallel to the xk axis. So at each point here, I know that this quantity is 0 by the inductive hypothesis, right. On the other hand, what this is claiming is that that this guy is actually parallel along lines parallel to the xk axis. Okay, so along each of these blue lines, this particular vector field is parallel, but this vector field vanishes at one of the points on that blue line. So then by our lemma 1, it implies that this vanishes on the entire blue line, but this happens for all blue lines. So this is 0 on all of Sk. For all j from 1 to k minus 1 and for all I. On the other hand, we already know that this is 0, right, for all I. So together this implies that this is 0 on Sk for all j from 1 to k and for all I. Okay, so this proves the claim and hence our main theorem on a characterization of flat manifolds. Alright, so that is it for this lecture. In the next lecture, in the next couple of lectures, I am going to introduce various different avatars of the curvature tensor, which are in many applications they are much easier to understand. rather than this sort of 1,3 tensor or 0,4 tensor. Okay, so namely we are going to introduce the sectional curvature and then the Ricci curvature and then the scalar curvature. So that is the main aim of the next couple of lectures. Alright, so that is it for this lecture. Thanks for your attention, and I'll see you in the next lecture. Thank you.